Okay, let's do part two. So here we're using some different techniques. So in the first part, uh, as with any instancing, we have a kind of um, almost like a class or the master form of the geometry that is instanced. And so we are determining the number of instances and this translate, scale, rotate, color properties with chops. You don't have to use chops though. So here I'm actually using this box with 8 points and then some noise on that to change the translate. So I'm looking at this null one SOP, and then instead of like a TXTYTZ chop channel, I am grabbing the X, Y, and Z point coordinates of that SOP geometry. So that's kind of cool. So we can kind of see very easily. So our sphere we have here is instanced according to where each point of this is. And we can also do that with tops and dats. So let's just dive into this new place here and let's recreate this. So let's do, I guess first let's just do like the box and kind of see. So by default, which I've mentioned before, so the box has 24 points. If we consolidate, now that just has 8 points. It has something to do with how the faces are kind of merged together. I don't really want 3 different instances of the sphere on top of each other, so I'm consolidating the quarter points here. So let's turn that on, translate up. Okay, and there we go, right? So that's just by itself, that's pretty cool. We can see that, right? So for each point, that generates a new instance. Cool. But let's see what's happening over here. So what? This is noise. Like how is that going to do something? So let's go back here. So now I see R, G, and B. So that is insane. So what we're doing, I've got a 10 by 10 noise grid here. So I've got 100 pixels. So really we're just thinking of this not as a visual thing. We're just thinking of red, green, and blue data. So if I go in here, pixel values, right? So like this one right here, we see the red, green, and blue values down there. Very easily, we can just imagine that as being XYZ, right? So it's really just translating the RGB to XYZ in a really direct translation. I have something else kind of happening here in my noise, at least in my display. If we go over here, so I did just kind of set these little things. In the comments, I made it 10 by 10. By default, we see it like this. So input smoothness and viewer smoothness is set to interpolate. So this is kind of like blurring. So it's not just for the display, but it's for the actual output. It's actually kind of blending that right there. But to maybe understand a little bit more clearly how these 100 pixels are being translated to that, I'm just doing nearest pixel, so it makes it nice and hard edged. Okay, and then also we'll notice here, so it's set to 32-bit float. Let's do this. Ooh, look at this. It's all kind of like weird and jittery. That's interesting, right? So suddenly, if I go back to pixel values, each of this red, green, and blue, they now only have 0 to 255. I mean, here we see it at normalized 0 to 1, but essentially there's still 256 steps from the darkest value to the brightest value for red, green, and blue. And that is leading to this really jittery spatial effect because it's just kind of like quantized like that. Which, to be honest, I'm not angry at that effect. It looks kind of cool. But just yet another example of how a difference between this 8-bit fixed and 32-bit float. In this sense, also fixed means it is definitely clamped from 0 to 1. Like there will be no pixel values less than 0 and or greater than 1. So that's what fixed means. When we go 32-bit float, like we calculated before, we've got 2 to the 32 power, so 4.3 billion steps in between that. And so I guess technically the end of that would be a kind of fixed clamp of like brightest and darkest, but not really, right? So we've got such detail resolution in between that. And see here we've got much smoother motion, of course. You can't really see it right there, but I do have a absolute time. That's what's actually making these move. Yeah, there we go. Okay, so and also actually one other little trick involving the display here. If you right click again, if you click viewer active, right click, view as points. So built in to our top, we can already see things as points in 3D space. So that's pretty crazy. View as image. And we can do that with any top. Here's our banana. Click view as points. That's the points of our banana there, spread out, RGB translated to XYZ. Okay, cool. So that is a wild little translate. DATs. Let's do this right here. So let's use this table, and then I've labeled these right here. So txty, tz. So maybe you have a huge DAT table with some sort of data. Who knows? So if each of these becomes an instance. So add row, -0.3. Right, whatever. So every row is going to become a new instance. So that's just to show that the instancing can be pretty flexible. You don't have to use just chops, and you could use like any combination of things, right? So let's maybe go back to this box here. Or actually, no. Let me go through this situation that I had before. It's null. And maybe I'll go ahead and call this translate. Actually, you know what? Let me just experiment with this. This n means normals. Okay, so those are not moving. Just making sure the normals should not be moving, I don't think. But what if I did point normals? Okay, so that's a little different. Because see, look what happened here. So if I do display options, normals. So this noise now is not changing the point positions, it's changing the point normals. Looks like a little bug that's flipped up on its back or something. It can't walk anymore. So then over here, instead of looking at the points, I'm looking at the normals. So that has a different effect. Kind of like that actually. It seems like they're kind of flying around a centralized point, which they are. So many ways we can do all this. But the point I wanted to show was, we could have, some other, like a chop or whatever, determining the rotate or scale or whatever, because all these can look at different operators. So that's fairly freeing. Another point I want to show, by default, the instant count mode is set to instance ops length. So because this has 8 points, I created 8 instances, and I got into trouble when we do this. Is gonna not work, but whatever. It's right. So something like this, same number of instances, have the same length, blah blah, because this has 100 pixels and that had 8 points, right? We can get around that if we do manual. And now no matter how many, whatever the length is of the operator you're bringing in, it's going to create this many instances, whatever you type right here. So if I did, oops, didn't want to do that. So let's see what happens now, actually. Let me just keep that all the same, actually. So, okay, so now the scale is actually working because it's just taking, I got 5 instances, it's just taking the first 5 pixels from this, and it's just discarding the rest. So that could be kind of cool if you want to have, some various operators coming in, and then maybe you can control, this length in different ways. So that's a cool different thing you could do. Okay, I want to show how I did this little situation too. So this is kind of revisiting also the texture thing from last week to create a little line thing. So it's nice and easy thing we could do, or we can actually, let me go back to changing position. And let's go back to that. So we have all that. So I'm going to create, actually, let's do the null there, new geo. And instead of that, I'm going to do a line. So really quickly right there, we can kind of see by combining, by using a SOP as the kind of instance parameter operators, and then we kind of translate it, we kind of swing it down over here to use it as actual geometry also in some different material. You can combine things to create some pretty cool effects. Okay, so have fun, experiment.